All right, thanks, Dennis, for the invitation. So today my talk is about acceleration and more precisely about how we can accelerate the way we perform simulations. But actually, let me start with like a rhetorical question, which is, how would it change your life if you could do something that's 40,000 times faster? So just to put that in perspective, you could grow a tomato by the time you plant the seed into the ground to the time you can basically slice it into your plate in about 3 minutes. Or you can fly from New York to LA in about half of a second if you could do it 40,000 times faster. Or you could get your undergrad and graduate degrees in about 50 minutes. So this is the type of acceleration that we're trying to target. And so in matter of parlance, we're basically interested in accomplishing this type of acceleration to accelerate the way we can simulate and predict different types of materials processes. Where basically, in this case, I'm going to be talking about two problems. So the first one is about predicting microstructure evolution and its associated properties. And so I'll be talking about how we can use different types of like machine learning strategies to accelerate phase field simulations, which can be applied to like, many different types of problems where you can basically trying to link process to structure. So it can be, for example, related to like physical vapor deposition, grain growth, solidification problems, or phase separation problem. And the second type of problem is more related to computational mechanics. So if we can rapidly predict the effect of microstructure on structure in the context of like co-designs of materials or in the context of FE² modeling, then maybe we can start using this type of like accelerated scheme to explore a much broader input space. So if you look at like existing phase field models and FE² strategies, they are basically inherently computationally expensive. And they are expensive because you have to solve a system of like coupled partial differential equations for a set of like continuous field variables or different types of field that describe these processes. And so far, most of the current effort to minimize the computational cost have been focused primarily on leveraging high-performance computing architectures and advancing numerical schemes to speed up these calculations. But throwing more computational power at the problem seems very simple, but it may not necessarily be the best solution, since computational cost-effective solutions decreases as the complexity of the microstructure evolution increases. So the more complicated the problem, the more complicated your implementation, and the less computation effective it's going to be. And so here we're trying to like basically coming up with machine learning architectures from which we can start from like high fidelity mesoscale predictions using some machine learning type of engine to accelerate this type of simulations, and yet keeping the same type of accuracy. So the first problem I'd like to kind of like illustrate on how it works is on a simple binary alloy phase separation evolution, where you start with like some sort of like a random microstructure that is defined in a Cartesian space, and that microstructure is basically going to evolve as a function of time. So that's what you see at the top of your screen. And so our problem basically is to kind of like learning, given like the history of like the microstructure that I'm going to call like U, is can we formulate this microstructure evolution problem as being equivalent to learning a mapping function. So that's what you see at the bottom of your screen is like, I'd like to like basically learn a mapping function that tells me how that microstructure evolved. And so for this, we need basically three ingredients. We need an efficient way to like learn a low dimensional representation of that macrostructure. Once we're able to do that, then we can evolve this representation via some like history dependent machine learned algorithm, and then use these machine learned dynamics to leap into time. And that's basically the three ingredients that you need to basically coming up with this sort of acceleration. So on the first ingredient, the first foundation for this is based on the so-called like manifold hypothesis, which basically states that like any high dimensional data sets actually lies on some low dimensional manifolds inside that high dimensional space. And then you can use that manifold structure as one of the elementary building blocks for acceleration. And so as a consequence of this manifold hypothesis, many data sets that appear to be initially requiring a lot of like variable to describe it can actually be described by a comparatively very small number of variables. So if you apply this like manifold hypothesis and use different types of dimensional reduction on that first macrostructure evolution problem, this is what it looks like. So here I'm showing you a comparison where we compared different types of dimensional reduction on our macrostructure evolution problem. So what we did is we took our macrostructure, we came up with like a statistical description of that macrostructure using like 2-point correlation. And then on that 2-point correlation, we basically applied different types of techniques. So we use like principal component analysis, which is just like a linear embedding technique. And then we contrasted that with like 3 different types of nonlinear embedding techniques, so-called isomap, umap, and auto-umap. And so what you see is that if you focus your attention on the PCA, you see that like for like all the different trajectories that we had like a very smooth description of the macrostructure evolution in a low dimensional space. But if you look at like the nonlinear embedding techniques, so isomap, umap, or auto-umap, you see that like you don't have as like smooth descriptions for the macrostructure evolution. And actually what happened is the isomap, umap, and automap, instead of like providing with like this like smooth description, what they did is actually they provide you some sort of like a clustering of like these different trajectories based on like how the input space that describe each of these trajectories is set up. And so that's not necessarily like what you need. So like one of the takeaway from this is that if you want to use any dimensional reduction technique to accelerate your direct numerical simulation, and if you're going to use this basically in your setup, you probably want something that is smooth. And so in our case, we decided to go with like the statistical representation of the macrostructure coupled with PCA as our building block for acceleration. So what you achieve by doing this is like you start with like a macrostructure. In this case, that was like a 2D type of simulations, like a 512 by 512. And you can basically reduce it to something that would be like a much lower dimension. So in this case, we only needed to keep like the first 10 components of our principal component analysis to basically capture over like 98% of the variance in our entire data set. So that's basically already like a reduction in terms of like the compact representation of like this macrostructure evolution by 26,000. So this is like what I just showed you before is basically, again, you use like some sort of like a statistical description of your macrostructure. You use some like embedding techniques. In this case, like PCA works relatively well. And then we're going to use this as like a building block to basically learn the dynamic in that reduced space. But you can also use something different. Where we can also use an autoencoder to basically do exactly the same thing. And so here, again, this is like a different strategy in terms of like the way you can embed your macrostructure evolution. And in this case, we basically trained an encoder to basically give us like a fairly low representation of a given macrostructures. And then the decoder basically learns how to take this like lower dimensional representation of the microstructure to reconstruct the microstructure in the primitive space. And what we're using again as our building block for like learning the dynamic is going to be that like latent representation. And I'll kind of like contrast like both techniques as to like, you know, which one gives us the best results. So by using an autoencoder, basically what you've done is like you transformed some data that is not trainable into like a trainable distribution. And it's a trainable distribution, which is, by the way, also insensitive to noise, which is like one of the advantages of like using autoencoders. So that's like that's the first ingredient. Again, we started with like a given microstructure that evolves in time, and we want to basically at like any given time coming up with like a compact, low-dimensional representation of that microstructures. You have two options: using statistical representation combined with some embedding, or you can use directly an autoencoder. So the second ingredient is how do we do our time forecasting? So in that case, you know, you want to use some history-dependent machine learning technique to learn the time evolution of that low-dimensional representation. And again, so the mathematical foundation for how this is going to work is basically based on the universal approximation theorem, which basically states that like any continuous function defined in an n-dimensional unit hypercube may be approximated by a finite sum of the type that what that looks like on the right-hand side of your screen. So if you translate that into you know, a neural network, basically what this theorem is telling you is that a neural network can basically be used to approximate any continuous function to arbitrary accuracy with when no constraint is placed on the width of the network. So again, in this case, our n-dimensional unit hypercube is our latent representation of the microstructure. And now we want to use like a neural network to basically, you know, learn that dynamic. And so in what we've done, we've explored two different types of method. The first method is based on recurrent neural net. If you look at like the literature on recurrent neural net, there's basically like different flavors and complexity ranging from like a simple RNN, but generally these are not necessarily like very useful because they tend to be prone to like the so-called like vanishing gradient. And then you have like more advanced architecture based on a very simple like vanilla RNN, so like the gated recurrent unit or GRU. Which has a fairly simple architecture to kind of like keep track and carry in some memory. And then you have like a much more complicated architecture, which is the long short-term memory neural net or LSTM, which again has like also the ability to kind of like carry that memory of the microstructure. So in this case, again, we're basically taking our latent representation of the microstructure, use that as an input, and we basically want to be able to like predict the evolution of like that latent representation of the microstructure in time. So what we've done is, again, compare different types of architectures, and we basically fed the history into these like neural network. And so what you see on the right-hand side of your screen is basically as you quickly increase the complexity of your network, you're going to start to like basically overtrain and overfit your network. So you have to like basically reach a balance basically between the complexity of the network. So in this case, like the number of cells, and also, you know, how many time frames you need to have to basically get like a good accuracy on the predictions of your microstructure dynamic. And so that's what you see at the bottom of your screen, where in this case, we needed to like train our network for at least 80 time frames before getting an accuracy with respect to like the direct numerical simulation that would be less than like 5% difference. And so what you see is that once your neural network is trained, you basically have similar accuracy as compared to like high fidelity phase field results. So the results at the bottom showed you for like, basically predicted timeframes that have not been seen by the network, that both for like the training and testing data set, we can achieve a difference between the predicted microstructure evolution from the neural network. And if we compare that to the direct numerical simulation phase field results, that again, we get like less than 5% difference between these two. And these for like over like 10 time frames, which is a lot of time. And that we can also basically capture both like the short range and long range interactions in terms of like their evolution in the microstructure evolution, which again gives you, a very good accuracy. One other thing that actually initially before we tried was like you say, well, do you really need an RN strategy to achieve this type of results? And so if you look at like the classical time series extrapolation technique in applied math, actually people have been using like this like so-called like TSMRs, so time series multivariate regression splines. If you were to use that type of technique on your latent representation, what you see is that you would like accumulate errors over time, which is not something that you want. And so that's not very good for extrapolation of your data. However, if you use like a GRU or an RNN type of or an LSTM type of architecture, what you see is that that's the results on the right. You actually get like very good extrapolation on your results. I'm going to skip that. The second method that we used was not based on RNN architectures, but so-called on like deep operator network. And so deep operator network, it's like a different thing where basically you try to like learn the operators that effectively solve your PDEs. And so DeepONet was initially developed by George Karjanakis at Brown University. And this type of architectures is basically divided into like two networks that are merged together. You have the branch net that basically approximate the functions and related to the inputs. And then you have the trunk net that basically does the same thing, but for your output. And then you basically do like a combination or like a product of these two networks to basically approximate your operator. So in this case, we did that where we used our autoencoder architecture to describe the microstructure. And then that latent representation was fed into our DeepONet architecture. And the DeepONet was basically predicting the evolution of the microstructure when learning that mapping in the low dimensional space. And then once you have like the evolution of like your low dimensional space, you can use your decoder to basically retrieve at some point your microstructure. And so what you get from this is basically an efficient surrogate model that also predict the microstructure. So here what I'm showing you on the screen is like the top row shows you the evolution of the microstructure as predicted by the high fidelity phase field simulation. The middle row shows you the predictions given by our DeepONet architecture. And the bottom row is showing you basically the difference between the two. And so what you see is that overall, we have like a very good agreement between predictions given by our DeepONet architecture as compared to like the direct numerical simulation. Recently, we've been looking at like more complicated problems, which is like problems where the size of your domain would change as a function of time, as a function also like the microstructure basically change. And so in this case, we had to change our architecture slightly, where instead of like first training the autoencoder on our training data set and then training the DeepONet, in this case, we had to come up with like a concurrent training dimensional reduction / ML engine to basically capture the moving boundary, basically, and at the same time capturing the way the microstructure evolution changes. And actually what you get is now this type of results, where on the left-hand side of your screen, you see the evolution as predicted by the phase field simulation. The middle evolving microstructure is the one as predicted by our concurrent strategy. And on the right-hand side is basically the difference between the two. And so what you see is not only we're able to like capture accurately that moving boundary, so like the size of your domain basically keep changing as a function of time. And at the same time, we're able to like accurately capture the formation of like the microstructure, which changes like at a much slower time scale. So, you know, based on this, the next question and the final ingredient is like, well, how do we leap in time in direct numerical simulation? And so the strategy is fairly simple. It's like you can basically feed back your predictions directly into your direct numerical simulation architecture as a way to kind of like smooth out your reconstructed microstructure, but also it kind of like some sort of like a balance and check to kind of basically course correct the physics. So here I'm showing you an example using our first method, where if you just keep running your LSTM architecture and trying to predict evolution over like long time scales, the reconstructed microstructure is not so great. However, if you take that microstructure, feed it back into your direct numerical simulation framework, what you see is like not only like you kind of like smooth out the microstructures, but you also kind of like improve the accuracy as compared to like direct numerical simulation. So, you know, in a nutshell, the way this like leaping in time works is you start with like a given microstructure. You use your machine learned engine to kind of like leap in time and then go back in direct numerical simulation, basically bypassing all these like very expensive time frames that you would get from like direct numerical simulation. And so, you know, one of the hybrid scheme that we came up with is as follows. So you can basically run your machine learn engine for X number of seconds. So in this case, that would be for like 2 seconds. That would basically correspond to like predicting about 20 time frames, and then feed it back into your direct numerical simulation to again simulate 20 time frames and back and forth. And so this is kind of like what you see here is that you can kind of like leap in time that way. In this case, we didn't do any optimization on like what is the best amount of time that you need to spend using your machine learning engine, or like the amount of time that you need to like use to using like the dynamic simulation. But what you see is that that's a way to kind of like leaping in time. And so in terms of like performance, what you see is that we can replace solver for an interpolation task or acceleration predictions for extrapolation task. And so if you were to run 50,000 simulations for 5 million time step per simulation, if you were to do that using just high fidelity phase field modeling, it would take you about 9 years. Granted that like our phase field code necessarily doesn't have like all the bells and whistles in terms of like time integration, but still it would take you many years to kind of like run 50,000 simulations. But with our accelerated machine learning engine, it takes us about 25 to 50 minutes to do 50,000 simulations for 5 million time steps. So if you do the ratio between the two, you basically get an acceleration of about 45,000 times faster, which is again like pretty impressive. And you know, there's like a lot of things that you can improve on. The second problem I wanted to kind of like briefly touch on. So everything that I talked about so far is about microstructure evolution, but you can apply the same type of concepts to classical continuum mechanics. And so here, I don't know if you know Augustin Louis Cauchy, who was like a very famous French mechanician, but I'm sure he would ask us the questions like, well, how can machine learning techniques learn a mechanics problem? And so in our case, we're interested in basically learning the mechanical behavior of composites across scales, where you would basically have some deep learning architecture where you can fit in the individual components of either like inclusions and a matrix, or at like a different scale, a matrix and fibers, and basically being able to like predict the effective response across scales. So in this case, we borrowed some work that was done by Liu and coworker work at ANSYS, which is called like the deep neural network, where you can basically learn the topological thermomechanical response of an RVE using some deep neural network. And so what I'm showing you on these slides are basically the components on how it works. So this architecture is a little bit specific, and it's physics informed because the operations are done at the neural level are based on classical macromechanics and homogenization rules. So you can define basically a relationship between the macro stress and the local stress. You can define a relationship between the macro strain and the local strains. You can define a relationship based on the Hill-Menden principle that basically gives you the equivalence between macroscopic conservation of energy and like what you would get also from like your local field, and so on. And so again, instead of like having like classical operations such as like multiplication, division, subtraction, etc., done at the neural level, now you're using like macromechanics rules to kind of like pass the information. So the power of this type of like network is that you basically train your data on elastic data, which is fairly cheap to basically generate. And once your network is trained on elastic data in the offline mode, then in the online mode, you don't need any retraining. And instead of like using elasticity rules to kind of like coming up with the relationship or the effective relationship that's given by the network, you just need to change the constitutive behavior at the neuron level, again, without any retraining, to basically being able to like predict the nonlinear response of your RVE. Just to kind of like walk you through some of the steps, as I mentioned, we had to like generate our data on elastic data. So in this case, I'm just going to give you an example of like this like very simple composites, but you can basically randomly sample properties for the matrix and your inclusions. In this case, we're collaborating with like my colleague at Los Alamos, Ricardo Lebenson, using his FFT-based simulations to rapidly predict the effective elastic properties of these composites, and then using that information to basically train our network. And so this is the type of results that you get. Is on just like the trained data, what you see is that to predict both the elastic constants and the coefficient of thermal expansion, we basically had less than like 1% error between what was predicted by the network and what was given by the FFT direct numerical simulations. And what you see on the right-hand side of your screen is actually like the real power of that network is that the comparison between the direct numerical simulations and our predictions from our network, when we want to predict the elasto-viscoplastic response of that composite, which is, again, you can barely see a difference between the direct numerical simulation results and those obtained by our network, which is very impressive. One of the things that we've been working on recently is trying to provide also explainability to the network. Because this network is based on macromechanic theory, we can use that to kind of like basically understand what the network is learning and how is the network interpreting the data it's been trained on. And so what you see on the left-hand side of your screen is a representation of the network. So like all the nodes and the information that's being carried by the nodes, we can translate that into like an equivalent learned microstructure by the network. And so what you see is that very rapidly during the training, the network is going to start to converge towards some, fairly complicated microstructure, which it thinks that it's the equivalent RVE from the original RVE. And what you see on the right-hand side of your screen is based on this learned DMN RVE, what we learn along the way is that it's also providing us a way to kind of like not only connect the macroscopic response as predicted by the network, but that also then provide us a way by which we can also extract information on like the local field distribution as predicted by the network. And so what you see from here is that that's on the very right-hand side of your screen is that the distribution of like local fields as predicted by the network basically corresponds almost exactly to the distribution of like a local field as predicted by the direct numerical simulations. The only difference is going to be in the tails. If you notice, the microstructure predicted by the network has like these like very sharp inclusions, which you don't have in the original RVE. And these like sharp inclusions, basically the distribution of like local fields shows up in the tail end of like the distribution of like the local fields. And so in terms of acceleration, using this type of physics-informed architecture, you can basically evaluate, again, as an order of magnitude, you could evaluate 10,000 composites in about 10 minutes, as opposed to like two plus years if you're to use like high fidelity finite elements. So again, in this case, it's not necessarily like 40,000 time plus acceleration, but it's still 4 order of magnitude acceleration. So in conclusions, I think what I wanted to illustrate here is this is what happens when somebody like me with like a computational material science background try to use a machine learning method. I had to work a lot with like folks from like, computer science, data science, and this is generally how I feel when I talk to these folks. I'm kind of like the big bird in the room, but at the same time, I think I come in with like a very different perspective, coming up with interesting intersection. There's still some work to be done though, in terms of like what we've done. On the first ingredient that I talked about to describe the microstructure in a latent space, some of the challenges that we discovered is that if you move away from like this like fairly simple type problem that I just talked about, and you want to capture like different types of like length scales and different sort of like short versus like long range interaction in your microstructure as it evolves, that becomes a lot more complicated. And so some of the dimensional reduction techniques that we've been using are not necessarily the most appropriate. The second challenge is related to the second ingredient, which is on like learning the time evolution using this like, physics-informed time-dependent algorithm. And there's basically two challenges here. Again, everything that I talked about was based on synthetic data. But you can think about now if you have like multiple fields evolving at the same time, you probably also want to be able to like learn the dynamic that describe the cross evolution and the way these like different fields would interact. And this is something that we're working towards on, but which is highly non-trivial. And the second challenge, which is more like an aspiration than a challenge as of right now, but one of the things that we're trying to think about is like, how can we fuse modeling with like experimental data? So now you can think about if you have like sensor data that's like in the field for like some microstructure that evolves, can you retrieve that data and use that and ingrain that into your machine learned dynamic evolution solver to kind of like basically coming up with like predictions of like where this is going to go. And again, this like fusion of like modeling and experimental data is highly non-trivial, but that is something that we're thinking about. And so with this, I'll just like open it up for comment and questions.